Welcome to part 2 of our lecture. It's set up here. All right, so just to verbally kind of review, we talked about carboxylic acids and the nature of their reactivity. We talked about naming and things like that, and some acid-base chemistry. And now we're going to jump into some reactions of carboxylic acids. So 13.6 is the Fischer esterification. Again, the terminology isn't so important, but we're going to form esters. So give you a couple reactions here first, and then we'll go through a teaching mechanism. You take a carboxylic acid, alcohol, add H2SO4. This is a catalyst as usual. It's a very strong acid. And we're going to generate an ester. We're going to lose water in the process. So the loss of water, you can, as I'm talking, you can kind of start to think about which oxygen the water will come from. We'll see that with the mechanism. Let's do another example. Carboxylic acid, alcohol, H2SO4, catalyst. Both of these are esters. This reaction will serve as a nice introduction to a key reaction that we'll go over called addition-elimination. Before we show the mechanism, let's do a couple intramolecular. So that means the alcohol and the acid are on the same molecule instead of separate molecules. Again, 5- and 6-membered rings are favored. This one forms a 5. This one forms a 6. So the same idea, you're forming an ester. We call these lactones because it's just the name of cyclic esters, but we form these rings. So let's go over a teaching mechanism. Walk through this. Let's draw out all our bonds, electrons. 2 lone pairs on each oxygen. H2SO4 is a catalyst. Here we're going to have excess methanol. That's going to help drive the reaction. Again, you should be able to recognize this reaction without the excess or the catalyst. Okay, but I will try to put it in there. And we're going to form an ester. So it's a teaching mechanism. We'll skip what we've talked about several times. When we add an alcohol into excess alcohol into with an acid, dissolving the acid in the alcohol, you get protonated methanol. And you get the sulfonate, we call it. This is your active acid. We're going to actually regenerate that acid. So the cool thing here is that although we have a carboxylic acid proton that I've circled there, its acidity is about 5. Okay, so what we're going to see here, pKa of 5, and this here has a pKa of negative 2.5, give or take. Sulfuric acid is negative 7, so this is rapid. Now you have a strong acid pKa of negative 2.5, and so this carbonyl is going to pick up this proton. It's going to protonate a carboxylic acid, which is different than what we've been learning. We've shown acids giving up their proton. Now the carboxylic acid carbonyl is acting as a base. This is happening here to protonate we have our sulfonate still. Run out of room there. Same counter ion. So what do we have? Methanol now. Come in and attack. Add to this carbonyl, similar to adding to an aldehyde. The alcohol attacks. The electrons are pushed up. This is called addition. You get a tetrahedral intermediate. Right? Proton transfer. One oxygen to another. Again, we call this intermolecular. I've said this in several cases. I'm going to put this arrow and say this is not what happens. This would be a 1, 2, 3, 4-membered ring. Okay. Notice there's 2 OHs, so we can put the OH, we're going to form water. We can put it anywhere. We'll put it down here instead. Same idea. These are identical OHs at this point. So let's draw that proton transfer from this oxygen that I've shaded over to this one that I put an arrow. We're going to have a good leaving group. Water form. Equilibrium. It can go back and forth. Now we've got a good leaving group of water. We've got excess methanol that's going to drive this reaction. These arrows push down. We call this elimination. We're eliminating a molecule of water. Taken as a whole, this mechanism is an addition-elimination reaction. Minus water elimination. Got the sulfonate all the way through. Again, we're unlikely to reform sulfuric acid. We have excess methanol here. And that will help us regenerate our active acid. Possible that a carboxylic acid itself would simply pick up this proton, whatever the case may be. This is regenerated. At some point, a proton is regenerated and donated to another molecule of carboxylic acid so that this can finish its cycle. Again, big picture here. Got acid-base chemistry that is different than what we've seen with this carboxylic acid proton. And then we're adding and eliminating. Addition, elimination. We'll hear that term a lot. Again, there'll be a couple teaching mechanisms that will help us introduce addition elimination that we'll look at in chapter 14. All right, so that was 13.6, Fischer esterification. 13.7 is an introduction to carboxylic acid derivatives. So we've introduced carboxylic acids. Now, we already introduced them. Esters are derived from carboxylic acids. Carboxylic acid derivatives are very important. We're going to look at several of them. In this case, we're going to look at acid chlorides. Carboxylic acid chlorides. So instead of an OH, it's a Cl. So let's look at how these are made. Start with a carboxylic acid. Treat with what's called SOCl2 is thionyl chloride. You can form acetyl chloride. So acetic acid forms acetyl chloride. This is a carboxylic acid chloride. We call it an acid chloride for short. Same idea over here. Benzoic acid can form benzoyl or benzoyl chloride is how we name those. I'm not going to worry so much about naming. I think maybe we'll touch on that in chapter 14. But you can convert carboxylic acids to a lot of useful things. You can go to acid chlorides, and then you can use acid chlorides for a lot of interesting things. So let's go over, again, a teaching mechanism for SOCl2. We've got our carboxylic acid again. SOCl2 is a liquid. It'll be important in a second in our discussion. We will lose a molecule of OH essentially and add a molecule of Cl. We'll see the driving force of this is you're going to drive off gases, and we'll kind of show. We're going to add at sulfur here. And this mechanism is sort of an abbreviated or making assumptions type of mechanism. Okay, this is sulfur. Imagine a carbon-oxygen double bond. We can do addition to that, right? We've seen this. We're going to take this oxygen lone pair and add it. Probably technically this pair of electrons would be a little bit more nucleophilic, but we're not going to worry about that. We're going to use this OH. We're going to do addition. Form an oxygen-sulfur bond that'll end up being let's see what it'll become. Put our chlorines in here. The way to think about sulfur is 4 bonds plus a pair of electrons is neutral. We still have 4 bonds now with a pair of electrons. You can calculate formal charge for sulfur in much the same way that we've been doing all semester. We've got a plus charge and a minus now. Zwitterionic species. This is going to eliminate a good leaving group. We're going to talk about leaving group ability a lot in chapter 14. Cl minus is a good leaving group because it's a terrible base. That's basic. That's essentially how you correlate those things. So addition, elimination, again at sulfur. Put our Cl minus there. Again, there's lots of different ways we can draw this mechanism. You might see it drawn differently in the text or wherever. I don't remember how they draw it in the text, but this is a teaching mechanism for us. Excuse me, so that we can predict products. Yeah, I think I did draw it like they do in the book for that purpose, so that you could look at it in the book too. Okay. So here we got addition, elimination. Think of this as a very activated or reactive intermediate. Activated carboxylic acid this whole thing is a good leaving group, and we'll see why in a second. So Cl minus could come in here and deprotonate this H, but there's a driving force for this to add at carbon. So we did additional elimination at sulfur. We're going to do additional elimination at carbon. Let's show that. Add at carbon. We get another tetrahedral type of intermediate. Here's our Cl. Here's our leaving group. O minus zwitterionic species. This eliminates, I'm going to show it like this, elimination at carbon now. The carbon is involved in it is where the elimination is happening. All right, this is going to go to product. You can see that oxygen double bond forming chloride. This is all leaving, so let's show our leaving group. This is not a stable species. So essentially what's going to happen is you're going to lose SO2 gas and HCl gas. Again, the Cl minus is not coming around and deprotonating. You're driving off HCl gas and SO2 gas. Okay, there are entropic driving forces for this reaction to work. Entropy is driving this because we're increasing entropy by going into the gas phase, basically. So anytime you drive off gas, then you help push the equilibrium, much like we've talked about Le Chatelier's principle from time to time. But in any event, that's just some background so that you can kind of see. SOCl2 is a very special reagent. There's others too. But we can use SOCl2 to convert carboxylic acids to carboxylic acid chlorides. We introduced this reagent with alcohols very briefly. Again, just to introduce it, now we're talking about it a little more. You don't have to draw that mechanism, but you have to be able to predict products. Carboxylic acid, SOCl2 with heat. That's the triangle, so I'll put that heat there. Give you a couple kind of practice problems. SOCl2 and heat, you're just going to drive off HCl, SO2, and get the acid chloride. And we can have a double bond in there, things like that. All right, so that is introduced to two of the main carboxylic acid derivatives, esters and acid chlorides. We'll see something called anhydrides and amides in chapter 14, if not before. But first, let's go and talk about a reaction called decarboxylation. This is 13.8. So what is decarboxylation? Decarboxylation is loss of CO2. Loss of the carboxyl. Let's see what we mean by that. It only works with specific types of carboxylic acids. I'm going to draw this out. I'm going to use our alpha beta language here. We have an acid, and at the alpha position, we have two H's. And at the beta position, we have a ketone. We call this a beta keto acid. Can be any carbonyl over there. Let's put a CH3 just so you see that. It can be any, be a diacid. We'll show an example of that. But when we heat this up, when we have a beta carbonyl, that beta carbonyl will stay at the end. But we do a substitution. It's going to look like magic at first, but we're going to talk about a mechanism. So there's the alpha beta carbons. The zero carbon, if you want to think about it, this carbon and its carbon oxygens are gone. So we're going to lose CO2. And both, and also in, oh, that's not good. All right, we'll see how that works. Wi-Fi just disconnected, so hopefully I'm still connected here. All right, pause this real quick. I'm going to see if we are still connected. Okay, my Wi-Fi disconnected. Just give me a second. I don't want to keep going if you're not getting this. All right, looks like I'm still going. It says I'm still live. All right, let's take a chance. Keep going. It says I'm live. All right, I'm going to go back here from current slide. Not that you need to hear the play-by-play, but I'll put in a joke of the day here and see who's listening. All right, so we're going to keep going here with decarboxylation. Again, 5 and 6 membered rings are favored, and therefore they're favored in products and they're favored in intermediates. So we're going to redraw this. Of course. Okay, my pen. I'm going to redraw this in a 6-membered ring where the beta carbonyl is going to interact with the carboxylic acid proton. Remember, these are acids. They can undergo hydrogen bonding. This is an example of intramolecular hydrogen bonding. So let's envision, without drawing it, this oxygen that I'm circling here, these lone pairs are going to interact with this hydrogen to make a very stable 6-membered ring. 1, 2, 3, 4, 5, 6, including the hydrogen. And that is going to facilitate this. It's going to actually deprotonate. We're going to show this in an abbreviated way. What's really happening is these pairs of electrons, this pair of electrons is going to deprotonate here. We're going to show it as the ketone double bond. Pi electrons are going to deprotonate. These electrons are going to come down. There's your CO2 right there. Carbon dioxide. This carbon-carbon bond is breaking and coming over here, forming a carbon-carbon double bond over here. So we break this bond, break a sigma bond, forming a pi bond. These electrons are going up, so we have 3 arrows, and we can show this in a concerted way. This is concerted. We lose CO2. I'm going to draw CO2 in a funny way, even though it's linear. I'm going to draw it like this. Put carbon 4, oxygen 5 there. It's a gas, driving off a gas. What do we have? We form an enol. Remember we talked about the keto-enol tautomerization. This is a tautomer of the ketone. The equilibrium lies far toward the ketone. This is much more stable. This is intermolecular. We showed an acid-catalyzed version, but essentially these electrons are coming down, reforming the ketone. You're picking up an H from an enol, like another enol, for example. It's a good way to think about it, right? It's kind of a cascade process. You don't have to show all this. This is a test mechanism, with the exception of this last part. I'm going to circle all these 2 arrows. All you have to do is show me an arrow going from enol to keto. You don't have to label them as such. The key part of the mechanism is really over here. Okay. Again, you don't have to put in text to explain all that, but that's what's going on. All right. So decarboxylation. Show another mechanism with a diacid in a minute, but let's show some examples. keto acid, heat. Flue, all we're doing is heating this. It would probably be in some solvent. You get that. I'm going to put the H in there that was added. Of course, there was an H there before, but now there's two H's. What do we lose? CO2 gas. You wouldn't have to show that on a test. So let's give you another one. Now we've got a substituent at the alpha position. We can heat that and we can form a ketone. It's a very good way to form ketones. So that's decarboxylation. Let's go over the mechanism again with a different starting material, a diacid. And now one of the acids is going to stay because as soon as you form the product, a monoacid cannot undergo this reaction. We're going to heat it, and we're going to get carboxylic acid. I'm in the middle of something right now. Email me. Yeah. So we're going to get a carboxylic acid. We're going to get a monoacid. We're going to call this the keto, even though it's an acid, because we're going to see enol. We're going to see enol go to acid. Okay, so let's just show the mechanism. Alpha, beta. Same idea. We're going to rotate this bond. All we're doing is a bond rotation here. We're rotating the bond to put the H in proximity to the beta carbonyl so that we can show hydrogen bonding. It's implied there, okay? This acid proton is going to get deprotonated. This carbon-carbon bond is going to break. These electrons are moving over, forming a double bond. This pi bond is going to attack. Functionally, this pair of electrons is attacking here, and these are hopping up. Okay, but we're going to abbreviate that to show it as a concerted process. Okay, we lose CO2. Let's draw it linearly now. CO2, it's a gas. You don't have to say gas, but now what do we have? We have an enol. Oops, sorry, scratch that. An enol form of our acid. What happens with enols? They tautomerize to ketones or acids. Okay, it's the same mechanism given to you twice. This is a test mechanism. In principle, it's the same thing, okay? So let's show now what we can do with diacids. Same idea, looks different. Alpha, beta, got to have two carbonyls for this to work. Just heat, lose one of the acids, and you get a carboxylic acid. It's a nice way to make a monocarboxylic acid. Diacid, again, heat it, loss of CO2, carboxylic acid. All right. Let's go ahead and finish up and return to Bronsted acid chemistry, meaning H's are going to get transferred, and we'll introduce or reintroduce sulfonic acids. We've introduced this guy, para-toluene sulfonic acid. Again, we said this is the strongest organic acid we're going to see, pKa of -7, as same acidity as HCl, para-toluene sulfonic acid, call it PTSA. We're going to treat it with some generic base. What happens? This base deprotonates just like a carboxylic acid, but now we have 3 resonance forms that we can show. We can abbreviate the aryl as such. Right, just like a carboxylic acid, we can show this resonance. We draw it as 6 bonds to sulfur. It's a single bond there. This can push in, push these out, draw another resonance. So there's 3 resonance forms instead of just 2 like we had with the carboxylic acids. That accounts for the increased stability, right, of this anion. Okay, we have 3 oxygens to stabilize. Very, very, very weak base, just like the conjugate base of sulfuric acid. It's the conjugate base of para-toluene sulfonic acid. Very, very weak. Okay. So carbonyls get protonated. We saw that before with acetal formation. And we saw this with sulfuric acid that, let's forget the line there. When we had methanol, oxygens on carbon are going to deprotonate this. Okay, so the equilibrium here lies all the way to the right. Okay, poorly drawn, I apologize, but the same idea. It's just a deprotonation. What do we get? We get the protonated form of methanol, with a plus charge and a minus charge, right? This pKa is negative 2.5. This pKa is negative 7. The equilibrium is going to go all the way to the right. Again, this is no different than sulfuric acid. These are the same acidity. Okay. Look at the Fischer esterification. So sulfonic acids will donate a proton very readily to almost any oxygen. And let's look at a couple equilibrium problems to reinforce this a little bit. Use our para-toluene sulfonic acid. Amines will very quickly deprotonate sulfonic acids. Even more so. pKa of about 10 here. pKa of negative 7. So tremendous equilibrium to the right. Let's look at sulfuric acid again. Again, we know this. This is called dissociation with water. Just like HCl. Okay, I'm being a little sloppy, just trying to get through it. This is review. Sulfonic acids give up protons to things like water and ammonia. One last thing in this chapter, we'll call it quits. Recall, when we introduced this chapter, we said carboxylic acids, going back to carboxylic acids now, with amines will undergo deprotonation. Equilibrium lies to the right. Carboxylic acid is deprotonated, and you get ammonia, or an ammonium rather, I'm sorry. Okay. This is resonance stabilized, the carboxylate, and that's basically how we justify understanding this. Amines will deprotonate acids. Okay, so if they're on the same molecule, the same kind of thing will happen. This is glycine. You probably heard of it. It's an amino acid. It's the simplest amino acid. Now, instead of a 4-membered ring, we can show intramolecular deprotonation. This nitrogen will deprotonate the hydrogen and will form the Zwitter ionic form that is actually the stable or common state of amino acids at neutral pH. That's actually the favored form of amino acids at pH 7. Okay, so this is an introduction to amino acids. We'll come back to this later. This wraps up the carboxylic acids chapter, and we will see you on Tuesday.